Let's talk about the two comparison tests. So in summary here, the direct comparison test, as long as your series has positive decreasing terms, if you can show that you're less than or equal to a known convergent series, then you must be convergent as well. Or if you can show that you're greater than or equal to a known divergent series, then your series must be divergent as well. The limit comparison test answers the same question, which is just, does this series converge or diverge? But instead of having you do a less than or greater than comparison to something that you know converges or diverges, instead you still pick something to compare it to, but you compute the limit as k, or whatever the letter is, goes to infinity of your terms over the other terms. And if this limit doesn't exist, then the test is off. But as long as this limit equals a number, and that number is anything between 0 and infinity, for this test to work, the terms all have to be positive. So this limit, if it exists, is definitely, the smallest it could be is 0. So as long as this doesn't come out 0 or infinity, then both series, the AKs and the BKs, they either both converge or both diverge. So the idea is that you pick a series to compare it to that you know if it converges or diverges. So then at the end, you get to say that your series does whatever the comparison does. Okay, so I have two examples in this video. The first one, we're going to use both tests on it that you can see on the screen here. And then we'll talk about how you know if only one of these tests is going to work. Okay, so our first example, the question is just converge or diverge, that's it. And our series is k over k cubed plus 2k. All right, so if I just focus on the highest powers of k in the top and bottom, I have k over k cubed. So this gives me a sense that I want to compare to the series k over k cubed, which of course simplifies to 1 over k squared. I'm being a little bit lazy not putting the k plus 1 to infinity there, but exactly the starting point doesn't really matter for either of these. All right, so 1 over k squared as a series is a convergent p series. Here our p is 2. So I'm just going to note for myself, I know that the one I'm comparing to now is convergent. Okay, so if I do the direct comparison test, and I'm going to label this DCT, or direct comparison test, I would have to be able to show that the terms of my series are less than the terms of this comparison series here, which is something that is true here. So this will work, right? If I'm adding a little bit extra in the denominator and a bigger denominator, so a smaller fraction. So for every k, it's true that k over k cubed plus 2k is less than or equal to the same expression, but without the plus 2k, which of course simplifies to 1 over k squared. So by saying that our terms are less than these terms, we mean if you graph them, at least the dots that go with this series, so these dots are always underneath these dots. So the sum of all of these will be less than the sum of all of these. And we know that these sum to some sort of finite number because the series is convergent, and that's what convergent means. So if we're less than a finite number, we're totally a finite number. There's no way that these add up to infinity. So that is true. And the series 1 over k is convergent. So the series that we started with, k over k cubed plus 2k, is convergent as well. That's how we would answer this question using the direct comparison test. We also could have chosen to answer the same question and come to the same conclusion using the limit comparison test. So for the limit comparison test, and we put it over here in blue. I guess that color difference isn't showing up very well on the screen. This is a different color. This is blue. Okay, so I still need to have started with the stuff in red here, choosing to compare it to 1 over k squared, acknowledging that this is convergent. That's how this test starts too. But instead of worrying about things being less than or greater than each other, I'm going to jump into computing the limit as k approaches infinity of the ratio between the terms of the two series. So I usually write my term divided by the comparison term, but it actually doesn't matter. You can put this one on top and this one on the bottom, and your final conclusion will be the same no matter what. All right, so if I have my term, I have k over k cubed plus 2k, and that's all divided by 1 over k squared. We have a fraction divided by a fraction, so I'm going to write it, put a little bit of space here. I'm going to write this, instead of divided by a fraction, I'm going to have times the reciprocal of this denominator fraction. So I keep the top fraction. I'm going to do times the reciprocal of the denominator. There is some cancellation that we can do here. We don't have to do it, but if you realize there is a k on top and on the bottom that we could have canceled, and really we could have canceled it from the very beginning, but whatever. We could make this a k squared and a 2. I'm actually going to leave it. I don't really need to cancel it to answer this question, but we'll all end up in the same place. What I can do if I don't bother canceling is at least combine k times k squared into k cubed. K cubed plus 2k on the bottom. This is one of those limits that we can compute with a couple of different ways. They'll all lead to the answer of 1. The quickest way to compute this limit is to realize we're looking at a rational function in k. So as k goes to infinity, we can just focus on the ratio of the leading terms, which simplifies to 1. So that's my limit. So this 1 coming out of here is not particularly special. The 1 doesn't directly inform our conclusion here. All we really care about for this test is that the number is anything not 0 or infinity. Any number in between, whether it's 1 or half or 72, anything that's not 0 or infinity tells you that these series do the same thing. All right, so I'm going to kind of note here, 0 is less than 1 is less than infinity, so this is a success. And now whether I decide convergent or divergent depends on what the comparison series did. So we said we were comparing to something convergent. So my series must also be convergent, which is the same conclusion we came to doing this with the other test. So we said, this is just a second option for answering the same question. All right, so in this particular problem, we had the choice between the two comparison tests. It turns out that when the direct comparison test can be used, so you can say less than convergent or greater than divergent, it tends to be faster. You don't have to worry about a limit or exactly the 0 or infinity business. So this tends to be quicker and arguably easier. But the limit comparison test works in a lot more cases. So if you're not sure which one is going to work out, this is the one that's much more likely. Because if this could do it, this could definitely do it, and this will have more options. And I do have an example of that in my second example here. So my second example is the series 2k over k to the 3 halves plus 1. All right, so again, I'm going to just focus on the highest power of k, top and bottom. So this tells me I want to compare it to the series 2k over k to the 3 halves. Or I could lose the 2. You don't really have to take times a constant with you here. So if we want to simplify this, instead of 2 over k to the 1 half, just 1 over k to the 1 half. I get this 1 half by subtracting these exponents. This is k to the 1 divided by k to the 3 halves. So one pair of them will cancel and I get a half left over here. So I've lost the 2. You could also have a 2 right here, and it just slightly changes your limit computation, but we come to the same answer no matter what. Okay, so this you could write as root k if you want to, but either way, we're going to notice this is a divergent B series. The series that you're comparing to, it's most often a P series, so we can kind of we can apply the P test and decide convergent or divergent really quick. Every once in a while, we do also see a geometric series show up when you do this same move. You kind of take the dominant things top and bottom, and it turns into a geometric series. Those are helpful here as well, because we do have rules about when they converge or diverge, so we can get that part of the answer really quick. All right, so in this case, the reason that the direct comparison test doesn't work, let's say we're considering the direct comparison test. The issue is that 2k over k to the 3/2 plus 1, because of this plus 1 in the denominator, if I remove it, I actually have a smaller denominator. So this statement is true. If this has the bigger denominator, then this is the smaller fraction. So all I can really say is that my series is less than a divergent series. And less than divergent is not one of the things that's helpful here. We would need to be above divergent to make a conclusion in that direction. So the direct comparison test doesn't help us here. I will mention before I continue though, if this was a -1 right here, the inequality would go the other way and the direct comparison test would be successful. Okay. So this means that the limit comparison test is the only one that's going to get us all the way there. So we'll say limit comparison test. And we'll jump right into computing our limit. Again, I'm going to take the ratio of my series terms divided by this series terms, or vice versa. It literally doesn't matter. Again, I'm using the version without the 2. If you include the 2 in your comparison series, you'll just get a different number out of the limit, but the same function. Okay, so I have my terms divided by the comparison terms. Fraction divided by fraction. I'm going to clean it up a bit by just saying times the reciprocal of the denominator. There's no cancellation that can happen here. Depending on what formula you started with, there may be a lot of cancellation you can do here. For us, there's nothing. So all I'll do is combine this k and k to the 1/2. So that's k to the 1 plus a half. So we have 2k to the 3/2 over k to the 3/2 plus 1. And again, you can compute this limit a bunch of different ways. The shortest thing to do is just take the ratio of those leading terms. That simplifies to 2. So this limit is 2. You could also compute this 2 by dividing top and bottom by k to the 3/2 and then reassessing the limit. Or you could do L'Hopital's rule, considering it a continuous function, and take the ratio of the derivatives of these two functions. If all paths will lead to 2 in this case. Okay, so this 2 is a number between 0 and infinity, right? Only 0 and infinity would be bad news. So this is good news. This means that both of these series do the same thing in terms of convergence. Because I know one of them was divergent, that means they both must be divergent. So I'm going to conclude that my series that I started with is divergent as well. Notice that if you had used the 2 here, this limit would have come out to 1. Different limit, but same conclusion, right? Because we still got a number that wasn't 0 or infinity. So we still would conclude that both of these series are divergent.